Hi everyone. So in this video, we're going to continue to talk about polynomials, and specifically we're going to be focusing on something called zeros of polynomials. So we're going to start off by defining what a zero of a polynomial is, and what we'll see is that it's actually a concept that we've already looked at recently. It's basically just a new way of describing this concept. Okay, so let me jump straight into the definition. So a number C is called a zero of a polynomial f of x if f of c is equal to 0. So what is this really saying? It's basically saying that if there's a number, and we're using c to represent that number, that when you plug it into the function as an input, right here we see that c is the input. If when you plug in that input you get 0 as your output, then we call that number a zero of the polynomial. So I want to jump straight into an example so you can really see what this looks like. So I'm going to tell you right off the bat a fact, and then we'll think about how we could actually verify this fact. So I'm going to tell you that 2 is a zero of the polynomial f of x is equal to x squared minus 5x plus 6. So f of x is equal to x squared minus 5x plus 6, by the way, that is what's called a quadratic function, right? But we learned in our last video that quadratic functions are just a special type of polynomial. It's a degree 2 polynomial. Okay, so how could we verify this fact? How could we use the definition that is written in purple to show that 2 is a zero of this polynomial? Well, we just have to plug it in, right, and show that we get 0. So how could we verify this? We could say f of 2 is equal to, and then we can just see what we get when we plug that number in, right? So if we plug in 2, we get 2 squared minus 5 times 2 plus 6. And so what does this equal? This equals 4 minus 10 plus 6. And if you add all of those things up, you get 0, right? So that's exactly what this definition is telling us. If you plug a number in and you get 0, that number is called a zero of the polynomial. The main thing we're going to be doing in this video, though, it's not going to be, in this case, I told you what one of the zeros was, right? And then we checked that it was a 0 by plugging it in. But what I want to ask now is, how can we find all zeros of this function? So we're still going to be working with this same function. Well, let's go back again to the definition of a zero and think about how we could use that definition to find all zeros. So it's telling us that a number is called a zero if when you plug that number in, you get 0. And another way of saying that is that we want the output to be 0, right? And we're trying to figure out what are those inputs that give us an output of 0. So really what we have to do in that case is we would want to take our function and set it equal to 0, right? Because that would be saying that the output is 0. So I'm going to take this function and I'm going to set f of x equal to 0 and solve for x, right? Because that will tell us exactly what are the inputs that give us 0 as an output. So if we set this function equal to 0, this might start to feel familiar from videos, from our recent videos about quadratic functions. Because how do you solve something that looks like this? Well, you can either factor or use the quadratic formula. This one factors nicely, so we can factor it as x minus 2 times x minus 3 is equal to 0. And then from here we can get x is equal to 2 and x is equal to 3 by setting each of those. Maybe even, let me write this step down because I want to make sure you see exactly where this is coming from. You would set x minus 2 equal to 0, right? And then x minus 3 equal to 0. And we would get x is equal to 2 and x is equal to 3. And so that would tell us that what are the zeros of this function? Well, one of them is the number 2 and the other one is the number 3. So our answer here would be 2 and 3. Those are the zeros. So I said a moment ago that this might feel familiar. So I want you to pause and think for a moment and think about what other concept have we talked about recently that we gave a different name to it. We didn't call it zeros, we called it something else, but that seems pretty similar. So think back to what we've been talking about recently. Think about what would be another name or another kind of related concept that we found the same way. Well, it was x-intercepts, right? So when we were working with quadratic functions, we talked about finding the x-intercepts. And so the x-intercepts happen when the graph crosses the x-axis. So I'm just going to draw a quick little picture here. I'm going to write down this fact that I'm describing right now a little more precisely in a moment, but I just want to give you a quick visual. Like, for example, for this function, it would look something like this. And so these 2 points where the graph crosses the x-axis, those are called the x-intercepts, right? And so for the case of this function, those x-intercepts would be the point 2, 0 and the point 3, 0. And so basically, when you talk about the zeros of a polynomial, those would just be the x values. And when you talk about the x-intercepts, you're giving them as points, but really it's the same concept, right? Because if the definition of a zero says that it's a number that you plug it in and you get 0 as an output, well, that's exactly the same thing as the points on the graph where the y value is 0, right? Because outputs correspond to y values. So we're going to write down kind of a series of facts here that are all kind of equivalent ways of thinking about the same idea. So the following are equivalent. So this is a phrase that's used somewhat frequently in math. The following are equivalent. It basically means that for the next 3 things that I'm going to write down, if one of them is true, then the other 2 are also true. They're basically just different ways of expressing, again, the same basic concept. So the first one is what we wrote down, or what we first were describing in this video, which is C is a 0 of a polynomial f of x. So if C is a 0 of a polynomial, then that means that the point C0 is an x-intercept of the graph of f of x. So I know that these things, they probably seem like they're almost the exact same concept, and they really are. It's not a huge deal to differentiate between a 0 and an x-intercept. It's basically that when you're talking about the graph, that's when you're usually talking about x-intercepts, right? Because x-intercepts, you're talking about an ordered pair. You have an x-coordinate and a y-coordinate, and you're really describing x-intercept is talking about what the graph looks like. Whereas when you're just talking about the function, it makes a little more sense to talk about a 0 of the polynomial. But really these 2 concepts, or these 2 words, are pretty much interchangeable. This third fact is a little bit more different from these other 2, but it's also equivalent. So notice that we said that the 2 zeros of this function, right, x squared minus 5x plus 6, were 2 and 3. And so going back to this factoring step where we found those 2 points, notice that we had a factor of x minus 2 and a factor of x minus 3. And so in general, it's always going to be true that if c is a 0 of your function, then x minus c is going to be a factor of f of x. And this might seem kind of obvious because of how it played out here, but what we'll see in a later video is that we can actually use this fact to kind of work backwards. So it kind of goes both ways. So how did it work in this case? In this case, we factored and we used the factors to find the zeros, right? We first factored, then we used that to find the zeros. But it also works the other way. If you know the zeros, if someone tells you what the zeros are, you can use that to set up the factors. So it kind of, all of these three things, again, it's like as soon as one of them is true, all three of them are true. They're like interchangeable facts. Okay, so I want to do a few examples of finding the zeros of different types of polynomials. And then we'll also introduce another concept called multiplicity. That's basically just a feature of zeros of a polynomial. So let's start with this example. So I want to find all zeros of the polynomial f of x is equal to negative 3x cubed plus x squared plus 2x. Okay, so going along the lines of what we did in the last example, how did we find the zeros, right? We first did this, just to remind you, for this first example, we first did something where we kind of verified that a number was a zero by plugging it in. And so that's a good way to check. But how do you actually find the zeros from scratch? Well, you take your function and set it equal to 0 and solve for x. That's going to be our general method for all of the problems where we're trying to find zeros. So we're going to start by taking this function, setting it equal to 0, and solving it for x. So I would encourage you to, and this goes for all of the examples in this video, to pause and try to do the example yourself. And that way you can get a little bit more out of the example and see, once you've figured it out yourself, come back and see whether you got the same answer. And especially I'd say after we do one or two, then maybe the next one you can try it yourself. Okay, so how would we go about solving something like this? Well, as we've been doing with quadratic functions, the general method we want to start with is factoring. Now, the factoring is going to be a little bit different on this than it was on quadratic functions, right? Because this is not a quadratic function. Its highest power is 3, so it has a degree of 3. So there's one step that we have to do before we can kind of get into that more familiar method of factoring. And so that is, we can factor out something from all of these, right? So what can we factor out from all of these terms? Well, we can factor out x. But we can do something even better. So this is generally a good idea. Anytime you have a negative leading coefficient, it's always a good idea to factor that out because it will make the later factorization easier. So what I'm going to do is I'm going to factor negative x out from everything. So what are we left with when we factor negative x out? We're left with 3x squared minus x minus 2, or sorry, yes, minus 2. So you could have just factored out a positive x, and then instead you would have had a negative, positive, positive, and that's fine. It's just that, what's our next step? Our next step is going to be to factor this, right? And I think it's a lot easier to factor a quadratic expression like this when the leading coefficient is positive. So it just gives us an easier thing to factor as our next step. Okay, so how do we go about factoring something like 3x squared minus x minus 2? So maybe I'll kind of bring this piece off to the side here. So we've done a couple examples like this with factoring quadratic expressions where the leading coefficient is not 1. And we've basically talked about how guess and check is usually the most efficient method. So when I say guess and check, I basically mean setting up what you think the two factors could be, and we'll see that you can figure out that there's only really a few different possibilities, and you can just test those different possibilities and figure out which one gives you the correct answer. So if we have a 3x squared, we need to have a 3x and an x, right? That part is not up for debate. Then we need to figure out two numbers to go here and here that will multiply to give us negative 2. And so our options are basically positive 1, negative 2, or negative 1, positive 2. And so this is where the guess and check comes in, right? There's a few different things to try, but basically we don't need to worry about testing the first and the last term, right? We can just test the middle terms. And so in this case, our middle terms would be positive 6x and minus x. And so what would that give us as a middle term? That would give us a 5x. And we don't have 5x, we have negative x. So that is not the right choice. So we could try, if instead we were to flip the sign, it would give us a negative 5x, right? So if you just flip the signs of them, it's just going to flip the sign of your of the middle term. So maybe what we could try instead is putting plus 2 here and minus 1 here. So what would this give us as a middle term? It would give us negative 3x plus 2x. And that's what we want, right? We want negative x, so that's good. That's how that factors. Okay, so now we can go and break this down further. So we have negative x times 3x plus 2 times x minus 1 is equal to 0. And so from here, it's basically exactly like the earlier example, right? We can set each of these factors equal to 0 and use that to find the zeros. X minus 1 is equal to 0. Okay, so the first one, negative x is equal to 0. Well, if we multiply both sides by negative 1, we would get x is equal to 0. And so that is one of our zeros. For this one, we need to start by subtracting 2 from both sides. So we get 3x is equal to negative 2. And then we can divide both sides by 3. So we get x is equal to negative 2/3. And then for this last one, we just add 1 to both sides and we get x is equal to 1. Okay, so those are our three zeros, 0, negative 2/3, and 1. So I want to show you the graph of this. By the way, in our next video, we're going to be focusing on graphing polynomials, and so we'll get more into that. But I just want to briefly kind of use the graph to just verify that our graph looks correct. So here is this polynomial. So notice that the places where it crosses the x-axis, right, those should be the x-intercepts. We have the point 1, 0, we have the point 0, 0, and we have the point negative 0.667. So that's the same, that's negative 2/3. It's just rounding it here. And so we see that we do have those three x-intercepts. The other thing, and we'll go back and talk about this more in the next video, remember we had this idea of end behavior. So we talked about how the degree and the leading coefficient determine the kind of general shape of the graph. And so I'm not going to go into this right now because we're going to cover it in the next video, but if you remember the different rules for the degrees and the leading coefficient, you can see that this graph does have the correct end behavior that we would expect it to from the function. So I want to point out one thing that might have jumped out to you. So here we talked about how if a number is a 0 of f of x, then x minus that number should be a factor. And so the reason that this might have jumped out to you after this last example is that that's not really how things panned out in this example, right? So it did for some of them. So here we have x is equal to 0, and so that corresponded to a factor that was just x, right? Just x on its own. And that's the same thing as x minus 0. So that one's okay. And then over here, we had x minus 1, and that went with x is equal to 1. So that, again, that matches up with our expectations. The one that maybe doesn't match up with our expectations is this one, right? We got x is equal to negative 2/3, but the factor it came from wasn't x plus 2/3, it was 3x plus 2. However, that fact that we wrote down on the earlier page actually is still true. So I just want to kind of make a quick note here. So we had the factor 3x plus 2, right? So 3x plus 2. 3x plus 2, if you were to factor out a factor of 3, what would you get? So what would we get if we were to kind of pull a 3 out from these parentheses? Well, we would have x plus 2 over 3, right? That's how, if you were to multiply this 3 back in, how would you get this 2? It would be 3 times 2 over 3. So why am I telling you this? That tells us that our function also factors as the following. So I'm just going to rewrite the factorization, but instead of having this factor, I'm going to rewrite it as 3 times x plus 2 over 3. And then I'm going to pull that 3 out to the front. So you also could have factored it as f of x is equal to negative 3x times x plus 2/3 times x minus 1. So if you don't believe me, you could check this by multiplying it out, right? If you were to take this expression here and multiply it out, you would get the original polynomial. You would get negative 3x cubed plus x squared plus 2x. And then if you were to do the same thing with this, you would still get that same polynomial. So I would encourage you to try that yourself, just to really demonstrate to yourself that they actually are the same expression. So basically what I'm trying to get at here is that when you're actually finding the zeros, the factor that you may use to find the zero, it might not always look like x minus c, right? In this case, it didn't. It looked like 3x plus 2. However, this rule that we wrote down, it's not like I was lying to you. This is still true. Because even if the way that you factored it to find that zero wasn't exactly what you expected, there's always a way to rewrite it that way, because you can always kind of factor something out and rewrite it the way that that kind of matches up with those expectations. So that's not a super important point. If you're a little confused about that, don't worry too much. It's not really going to come up, but I just thought it was worth mentioning in case you noticed it. Okay, so let's do another example. And then after we do this example, we'll talk about this concept of multiplicity. So our next example is going to be to find all zeros of the following polynomial. So 2x cubed plus 12x squared plus 18x. And so even if you didn't in the last example, I would encourage you in this one to pause and try this yourself, and then come back and see if you got the same answer rather than just sitting and watching. Okay, so what is our first step? Well, if we're trying to find the zeros, we want to set the function equal to 0, right, and solve it for x. Okay, so before factoring, one thing that can be useful is to see, is there anything I can divide this entire equation by? Is there a number that goes into all of these factors? Because it basically will just make things easier to factor. So in this case, notice that everything is divisible by 2, so I'm just going to divide everything by 2. If you wanted to, you could also factor out a 2. It's not going to have an effect on your final answer, whether you factor it out or whether you divide both sides by it. You're going to get the same answer either way. So if we divide everything by 2, we get this. And by the way, let me just quickly mention that that's actually something you could have done on this one as well. So notice that the way that we handled this extra negative sign is we factored it out. If you wanted to, you actually could have divided everything by -1 before you even got started. And that might have made everything seem a little bit easier, like that makes this part a little more straightforward. You would just get x is equal to 0. But it's not going to have effect on your final answer. Okay, so just like the last one, we want to start by seeing what can we factor out from everything. So in this case, all of these have a common factor of x. So if we factor out an x, we're left with x squared plus plus 6x plus 9. And so now we're left with this part to factor. And so this one is a little easier to factor than the last example. So this one is just x plus 3 times x plus 3. And so what do we get as our solutions here? Well, we get x is equal to 0, x plus 3 is equal to 0, or x plus 3 is equal to 0. So notice we get kind of the same solution twice. So this first one is going to be x is equal to 0. This second one is going to be x is equal to -3. And this next one is going to be x is equal to -3 as well. So let's just take a quick peek at the graph just to verify that it looks the way we would expect it to. So again, if you think about end behavior and the degree and the leading coefficient, you would see that this does have the shape we would expect. And then we found that the two zeros were -3 and 0. And so we look and we see those are the two places where the graph has an x-intercept. Now you might notice that it's a little bit different. So if we look at this previous example, in the previous example, the graph actually passed through the graph at every single x-intercept. Whereas in this example, the graph is bouncing off at one of the x-intercepts and passing through at the other one. That's something we'll get into in our next video. It's related to the idea of multiplicity that we're about to talk about, but we're not going to talk about how it affects the graph until our next video, but I just wanted to kind of mention that to get the ball rolling in your brain about how the different ways x-intercepts can show up in the graph. Okay, so what is multiplicity? So the multiplicity, actually let me say it this way, a 0 C has multiplicity M if the factor x minus c occurs m times in the factorization of your polynomial f of x. So an example of this, and we'll actually go back and talk about multiplicity in the examples that we already did, but I want to just kind of give a quick example that can really illustrate a little more easily what multiplicity looks like. So let's say you have the function f of x is equal to, and I'm going to actually just write it down as though it's already been factored. So let's say your function factors as x times x minus 1 times x minus 1. And I just want to point out that there's another way that you could write this. You could also write it as x times x minus 1 squared. Either of those is an okay way of writing down this factorization. So if this was a polynomial and you were trying to find its zeros, well, you would find that its zeros would be x is equal to 0. And then you would also find that x minus 1 is equal to 0, which would tell you that x is equal to 1. And then you would get the same result from this one, right? That would also tell you that x is equal to 1. And so what's the difference in multiplicity? Well, for this first 0, so for x is equal to 0, notice that you only got that solution once, right? X only appeared once in the factorization. So what we would say about multiplicity is that this first 0 has multiplicity 1. And then what about x is equal to 1? Well, that one, notice, occurred twice. We got that same solution twice. Or another way of thinking of it is x minus 1 occurred twice in the factorization. And so this would be multiplicity 2. So I want to do one more quick example just to contrast with this one. So let's say that instead we had the function g of x is equal to x squared times x minus 1. And then another way of writing this, and this I'm kind of flipping the order as I did up there, but you could also write this as x times x minus 1. But I think especially with just something like x, we tend to write it as x squared, whereas for this one, you see people writing it both ways. But yeah, so let's say we were trying to find the zeros of this. Well, from here we would get, okay, x squared is equal to 0. And that's the same thing as saying that x is equal to 0, right? Or if you did it over here, you could say, just directly x is equal to 0. But because that solution appeared twice, right? Because we had x squared, or looking over here, we had x and another x, that tells us that this is a 0 of multiplicity 2. And then over here, we would get x minus 1 is equal to 0, and that would be x is equal to 1, and that would have multiplicity 1. Okay, so let's go back to the last two examples we did, and for each of them, just write down what the multiplicity is of each 0. So I would encourage you to pause the video and write down, figure out what these multiplicities are yourself. Okay, so for this function, we only had one factor that corresponded to each 0, right? Nothing was repeated. We didn't have anything squared. We didn't have any factor that appeared twice. And so that tells us that all of these zeros have multiplicity 1. Multiplicity 1. And this also has multiplicity 1. Okay, what about our next example? So in this case, x is equal to 0. We only got that once, right? It didn't come from an x squared, it just came from an x. And so that tells us that this first 0 has multiplicity 1. I'm just going to abbreviate that for the sake of space. So that has multiplicity 1. Now, what about these other two? Well, it appeared twice, right? We found the same solution twice. And so really, usually what you'll do is you won't write it down twice. You'll kind of just write it down once. And if you want, you can kind of do something like this just to really emphasize the fact that you got that solution twice. And then once you have that 0, just write down that it has multiplicity 2. Okay, we're going to do one last example that will bring in something slightly different. So the last function we're going to be doing is we're going to find all zeros of the polynomial h of x is equal to negative x to the fourth plus 4x cubed minus 2x squared. So just like on the earlier examples, I'd encourage you to pause and try this yourself. You'll see that something comes up that's a little bit different than in the last two examples, but it's something we have learned about, so I think you'll be good. And I think this would be a good kind of challenge to try to figure out this one yourself. Okay, so we want to start by setting our function equal to 0, right, and solving. That's the general approach for finding the zeros. Okay, so what can we do first? Well, one of the first things we want to do is try to factor out whatever we can. But remember earlier I mentioned that if there's a negative sign, as if your leading coefficient is negative, you can either choose to factor it out. That's what we did in this example. We factored out a negative x. But maybe an easier approach is actually just to divide everything by -1. So if you have a common factor in all of your terms, or if there's just a negative sign you want to get rid of, you can multiply or divide both sides by -1 or whatever you need to do to kind of simplify things. And so once we do that, we're left with x to the fourth minus 4x cubed plus 2x squared is equal to 0. And so now we can see what can be factored out. So notice that all of these terms have a common factor of x squared. So I'm going to factor out an x squared from everything. And we'll be left with x squared minus 4x plus 2. Okay, so this is where this one is going to kind of diverge from the earlier examples we did, because typically the next step is to take this part and factor it, right? But if you try to factor this, it actually cannot be factored. You're not going to be able to find two numbers that multiply to give you 2 and that add up to -4. So thinking back to quadratic functions, that the videos about quadratic functions, what do we typically do when we can't factor? We use the quadratic formula. Now I just want to make sure you understand exactly why it is that we're using the quadratic formula here. So remember that anytime you have a product of some things equal to 0, that means that one of those things is 0, right? So we could say either x squared is equal to 0, or in this case, because we can't factor this, our conclusion would have to be that x squared minus 4x plus 2 is equal to 0. Now, once we have something written down like this is where we can use the quadratic formula, right? You only use the quadratic formula when you have a quadratic equation where there's a quadratic function set equal to 0. It doesn't make sense to use the quadratic formula unless you have a quadratic expression equal to 0. And so now we do, but really from here, it is the right thing to use the quadratic formula, but I just really want you to understand that the reason you're using it is because you have this quadratic portion set equal to 0. One thing that I've seen a lot of students do that sometimes will actually give you the right answers, or at least some right answers, is kind of jump in and use the quadratic formula on this. But it doesn't make sense to use the quadratic formula here because you don't have a quadratic equation, right? You can only use the quadratic equation when you have something that is quadratic set equal to 0. So what would happen is if you tried to use the quadratic equation with this, notice that the coefficients are actually the same. If you compare the green and the orange, the numbers that you would be using as your A, B, and C would be the same. The problem is that if you jumped straight into the quadratic formula, you would actually miss these solutions. You would miss the fact that x could also be 0. So bottom line is you only use the quadratic formula when you have a quadratic equation equal to 0. Okay, so now we can use the quadratic formula for this part. So quadratic formula tells us that x is equal to negative b, so in this case that's negative 4, plus or minus the square root of b squared, so that's negative 4 squared, minus 4 times 1 times 2, so that's 4 times a times c, all divided by 2a, so that's 2 times 1. So in this case, that gives us x is equal to positive 4 plus or minus the square root of 16 minus 8 over 2. And so this simplifies to 4 plus or minus the square root of 8 divided by 2. And so we've seen that the square root of 8, that can be rewritten as the square root of 4 times the square root of 2, which can also be written as 2 times the square root of 2. And so we can rewrite this as x is equal to 4 plus or minus 2 times the square root of 2, all divided by 2. And now this can be simplified, right? So that we have a common factor of 2 in every part of the numerator. And so we can factor out a 2 from both terms in the numerator. And now this 2 can be canceled out because we're multiplying and dividing by 2. And so now we can write down these two solutions. So we have x is equal to 2 plus or minus the square root of 2. But remember, that's actually two different solutions, right? So one of the solutions is x is equal to 2 plus the square root of 2. And the other one is x is equal to 2 minus the square root of 2. So what about multiplicity? Let's actually maybe first go back, I'll circle these, and then we'll go back to the first 0 that we found and talk about the multiplicity there, and then we'll come back to this. So don't forget we have this initial part over here, right, where we said x squared is equal to 0. So what does that tell us? That tells us that x is equal to 0, and then that one has multiplicity 2. Oops, multiplicity 2. And so what about these two zeros that we found? Well, it turns out that if you get your zeros from the quadratic formula, each of them is going to have multiplicity 1. And for now, I would just kind of memorize that as a fact. We'll see in a later video exactly why that is. But basically, there's a relationship between the zeros and the degree. And what we'll see is that because the quadratic formula comes from a quadratic equation, there's really only space for each 0 to have multiplicity 1. So again, we'll get more into that later, but for now, just remember that anytime you're using a quadratic formula, each 0 that you find from the quadratic formula has multiplicity 1. There's one more thing I want to say here, and this is kind of a bonus piece of information. It's not super important. It's not something I'll test you on, but you might be curious, what is the relationship? So again, let me just go back to this front page. We said that anytime c is a 0, x minus c is a factor. And you might think that that is only true for zeros that are whole numbers, but it's actually also true when you get your zeros from the quadratic formula. So I'm going to kind of write this down as a fact. So our first 0 was 2 plus square root of 2, and our second 0 was 2 minus square root of 2, are zeros. That actually tells us that x minus 2 plus square root of 2 and x minus 2 minus square root of 2, that actually tells us that those are factors. And I know those look like kind of crazy factors, but let's actually use that to then write out the whole function. So what does this tell us if we kind of go back to how we originally started factoring the function? Well, one thing we need to remember is that we originally canceled out this -1. We divided both sides by -1. So really, if we want to write out the factorization, we should put a negative sign on it, right? We kind of got rid of a negative sign for the sake of solving, but if we're factoring, we should have preserved that negative sign. So our first factor would be -x squared. And then these two factors, I'm just going to distribute the negative sign in here and here on both of them. So this next factor would be x minus 2 minus square root of 2. And this next factor here would be x minus 2 plus square root of 2. So I'm not going to do this in the video, but I would encourage you as kind of a bonus, try to multiply this out. And you should see that when you go and multiply everything out, multiplying these two things together is a little complicated, but I would start with this. I would start, if you want to do this, start by multiplying these two things together, see what you get, and then multiply that by -x squared. And what you should see is that you get exactly the polynomial that we started with. So, again, going back to the point I brought up earlier, it really is true, no matter what zero you find, it is always true that x minus that 0 is a factor, even if that's not exactly the way that you actually found the 0. Last thing I'll just show you really quickly is the graph of this function. So this was -x to the 4th plus 4x cubed minus 2x squared. So we found that there was a 0 at 0. And then what are these other two zeros? Well, these you would have to find by plugging our solutions into a calculator, right? So we got 2 plus square root of 2 and 2 minus square root of 2. So 2 minus square root of 2 would be the smaller one. That's 0.586 approximately. And then the bigger one would be 2 plus square root of 2. So that's apparently 3.414. And then again, you can see, if you remember the rules with degree and end behavior, you can see this graph has the shape that we would expect. All right, so in our next video, as I mentioned, we're going to be talking about a lot of the same stuff in this video, but kind of putting all the pieces together with end behavior, zeros, multiplicity, and using that to sketch the graphs of polynomials. So I'll see you on that video.